Hi, I'm Daniel Davies from the GIO group at the University of Illinois in Urbana-Champaign. Today I want to talk about understanding polymorphic transition mechanisms of N-type organic semiconductors. First, let's talk about organic electronics, which are flexible in many ways. The organic semiconductors are soluble in many common solvents, allowing for high throughput, low energy solution printing. This allows us to access diverse form factors such as flexible electronics, and allows us to make flexible devices such as the Galaxy S Fold and create wearable devices. So, organic electronics offer a pathway to cheap, wearable electronics for diverse functions in the Internet of Things era. And one of the unique aspects of organic electronics is they exhibit polymorphism, where a single molecule can exhibit multiple different crystal structures. And Macron in 1965 famously said that the number of polymorphs is directly proportional to the amount of time and effort spent on that material. And we've seen that the crystal structure has an important impact on the optical and electronic properties. In this system here, under UV light, these crystals will emit green. However, once we go through a polymorphic phase transition, the new crystal structure quenches that emission. Similarly, in TIPS penicene, which is a high-performing p-type semiconductor, we can tune the mobility or how easily charges move through the material by orders of magnitude, just by small changes in the molecular packing. So control over polymorphism is key for full control over the optical and electronic properties of these materials. And one way to control polymorphism is through their transition mechanisms. So the typical transition mechanism is nucleation and growth. This is your classical molecule by molecule reconstruction of the crystal. And this tends to take on the order of seconds to hours, depending on which material you have, and is usually associated with large structural changes, a high energy barrier, and no shape change of that crystal. In a small but growing number of systems, we've started to see cooperative phase transitions. This, in contrast, is a displacive phase transition, where each molecule keeps its nearest neighbors, and this allows for an ultra-fast, on the order of milliseconds, phase transition. These are usually associated with smaller structural changes, lower energy barriers, and can even form changes in shape, such as in the case of shape memory alloys, where we actually see a thermosalient motion as the crystal will actually bend and move during the phase transition. So while cooperative transitions have been rarely reported in molecular crystals, they can enable dynamic electronic materials that weren't possible previously. And today I want to talk specifically about two-dimensional quinoidal terthiophene. This is a new high-performing N-type semiconductor. That is the reason these N-type semiconductors have lagged behind their P-type counterparts is because they require low-lying HOMO and LUMO levels. This molecule was obtained by adding these cyano groups as strong electron withdrawing groups to break the aromatic structure and form this quinoidal core. And then the alkyl chains were added to make the molecule soluble and prevent water and oxygen from interacting with the material in the solid state. And I want to talk specifically about two new phase transitions that we've found in this material. The first occurs at 166 degrees Celsius, and the second occurs at 222 degrees. The 1 to 2 transition we found to have a hysteresis, which is the difference between the forward and reverse transition, of 6 degrees. The 2 to 3 transition, however, had a hysteresis of 75 degrees, suggesting significantly different behaviors in each of these transitions, as these are related to the energy barriers. And that is exactly what we see. We see potentially two different mechanisms in one molecule. So in the 1 to 2 transition, if you blink, you'll miss it. The transition occurs all at once for this crystal, and as we can see, it's actually within one frame of the video, less than 0.1 seconds. In the 2 to 3 transition, however, we see some of the hallmarks of of nucleation and growth, where we see these nucleation sites and then a diffusive growth throughout the crystal that occurs on the order of several minutes, suggesting that we have two distinct mechanisms here. And we found that the molecules tend to pack in these one-dimensional pi stacks within these crystals. And between these layers of 1D pi stacks is where the alkyl chains sit. And you can see that the molecules actually have a significant tilt that appears to be associated with this, the tilt of the unit cell. So I want to look in more detail at the cooperative behavior of the 1 to 2 transition. We were able to track the structural changes using grazing incidence X-ray diffraction. And you can see that there's a smooth motion of these peaks from polymorph 1 to polymorph 2. This is indicative of that displacive type transition. And at the same time, we were able to extract a unit cell for both polymorph 1 and polymorph 2, and we can see that the main change is in this beta angle, which is representative of that tilt of the molecules with respect to the BC plane. At the same time, we also see a significant shape change to the crystals, where it shrinks by about 4% along the long axis. And this seems to be correlated to the change in the B direction, which is a decrease of about 3%. And this contains the pi stacks that we expect to be along the long axis of the crystal. And in the larger crystals, so on the order of a couple of millimeters, these crystals will actually bend and significantly move during the phase transition. And to understand why this cooperative transition is occurring, we look to Raman spectroscopy, which allows us a glimpse into what's changing at the molecular level in these crystals. And I want to look at this particular region as it contains two sets of peaks. So one set of these peaks are associated with the alkyl chains. So these are the CC stretching and the CH2 wagging in these alkyl chains. And then the other set is representative of the core CC stretching. So this is the ring breathing mode of the quinoidal core. And what we see is that upon phase transition, there's a significant decrease in the intensity of this peak, which we've represented as a ratio between the CH2 wagging to the ring breathing mode here. And at the same time, we see a significant redshift in this CH2 wagging vibrational mode. This seems to suggest that there's a significant change in the sidechain environment. And we suggest that this means the 1 to 2 transition involves a change in molecular tilt driven by rearrangement of the alkyl side chains. In stark contrast, the 2 to 3 transition has clear nucleation and growth type behaviors. So under grazing incidence X-ray diffraction, we see a decrease in the intensity of the polymorph 2 as the polymorph 3 peaks appear. And we see, based on the unit cell, there is a significant change in a significant reorientation of the unit cell. So previously we had a monoclinic type unit cell in polymorph 2, and this has become a trigonal or hexagonal type unit cell in polymorph 3. And again, we see a slight expansion of the crystal in polymorph 3, but this does not appear correlated to any of the changes in the unit cell structure. And finally, we see that there's multiple domains forming during this phase transition, suggesting there's no orientational or structural relationship between 2 and 3. Once again, we turn to Raman spectroscopy to understand exactly why this transition is occurring. And interestingly, we see a change in the ratio between the trans and gauche isomers of the CC stretching in these alkyl chains. So typically, when we see as this ratio approaches 1, that means the alkyl chains are rotating more freely and are in a more melted state. And at the same time, we saw the appearance of 2 new peaks. And these peaks seem to be at the expense of the quinoidal ring breathing peak. And as we can see, as the intensity ratio of the new peaks to the quinoidal peak increases, it appears that we're forming a new conjugated core. To understand this, we have to turn to one of the interesting properties of these quinoidal molecules, and that is that they have a biradical ground state. So, while we can force the quinoidal form using these strong electron withdrawing groups, the electrons, via resonance, will try to form the aromatic core again. And they do this by adding in stable radicals at these terminal carbon groups. And these radicals actually have interesting interactions. They're able to create these spin-spin interactions between molecules that are bond-like in character. They're called pancake bonds. So as you can imagine, a stack of molecules being pancakes, and then the electrons acting as the syrup to hold them together. And we can actually observe these biradicals under Raman spectroscopy, like what we saw previously, where there's the appearance of this aromatic stretching peak. At the same time, we can observe under electron paramagnetic resonance spectroscopy the increase in the number of spin centers that you see. So as more bioradicals are formed, there are an excess of spins in the molecules, and we observe that under EPR. And that's exactly what we see in EPR. As we increase temperature, we see a substantial increase in the intensity of the EPR signal, suggesting that we're increasing the number of radicals by about 20 times when we form polymorph 3. And so we suggest that as we increase temperature, we're forming more biradical species. And so we suggest the 2 to 3 transition involves formation of biradicals, which is driving the increase in core-core pancake-like interactions. And finally, we were able to harness cooperative behavior for novel electronic switching devices. First, we were able to create 2 terminal devices using single crystals, where we used P.PSS to attach the crystal at both ends. And we could change the conductivity of the system by switching polymorph. So as we heat it up to polymorph 2, we see a significant decrease in conductivity, which is partially recovered by forming polymorph 3. And then this is highly repeatable as we cool back down and see the reverse behavior. And then we were able to take advantage of the fact that between 1 and 2, there is a significant decrease in the length of the crystal. So we formed this system where at polymorph 1, the crystal is bridging the two P.PSS spots. But once we form polymorph 2, the crystal shrinks and cuts off interaction to one of the edges of the P.PSS. And using this, we were able to make a highly stable, thermally actuated device, where we could turn it on and off just by switching back and forth between polymorphs. So in summary, we were able to access a cooperative mechanism driven by side chain reorientation. And this is in stark contrast to nucleation and growth, which was driven by an increased core-core interaction. And for the first time, we have linked biradical formation directly to a polymorphic phase transition. And finally, we were able to harness the cooperative mechanism for highly robust actuator cycling. And in the future, we look to investigate how changes to the molecular structure affect these transitions. I'd like to thank Dr. Diao, Dr. Park, and Dr. Chung for all of their help on this project, the Zhu group for synthesizing the material for me, Dr. Ralph Weber for his help in getting in situ EPR data, and Dr. Gray and Dr. Woods for all of their help in obtaining the crystal structure for this material. If you have any questions, please feel free to ask me. Thank you.